Pete, have you seen the 2/3 cup measuring cup? I'm making pretchos and need to measure the cheese. Oh yeah, I forgot to tell you. In a show of solidarity with my ancient Egyptian mathematical brethren, I gave it away. Oh, and the 3/4 cup too. I don't even want to get into why you feel like ancient Egyptian mathematicians are your brethren, but you gave them away? Why would you do that? How am I supposed to make pretchos if I can't get just the right amount of cheese? No problem. 2/3 of a cup is the same thing as a half a cup and a sixth of a cup. A sixth of a cup? Where am I going to get one of those? Nobody has a sixth of a cup measuring cup. Not even eBay. No problem. A sixth of a cup is the same thing as a seventh of a cup plus a 42nd of a cup. What? It's true. Dude, you are definitely not getting any of my pretchos. Well, that's fine, because judging by the random amount of cheese I just saw you dump on them, I don't think I'd want them anyway. Listen here, King Pete and Common. Thou shalt not covet my pretchos. Hey, Noah, did you know that the ancient Egyptians actually used fractions all the time? I would assume so. Without fractions, how are you going to build a really cool pyramid? Yeah, that's right. I mean, that's probably right. I've never built a pyramid, so I can't really say, but I do know this. As widespread as they were, ancient Egyptian fractions were not like the fractions you and I both know and love. We do love our fractions. Yeah, they're totally vulgar. Yeah, they're... Wait, what? Did you just say vulgar? Yep. It comes from the Latin word vulgus, meaning common or simple. It's just a funny name for an ordinary, regular old rational number. You know, numerator on the top, denominator on the bottom, all that jazz. So, are you saying that Egyptian fractions didn't have numerators and denominators? That's right, and I think that's a good point of view to keep in mind. The ancient Egyptians used a special symbol for their fractions, and that symbol conveyed the idea of a single thing, a single unit, being divided into some number of equal parts. The fraction 1/4, for example, was drawn by writing 4 hash marks, which was how the number 4 was represented, and then drawing a mouth symbol floating above it. A floating mouth? Personally, I think it looks more like a UFO, but everyone else calls it a mouth, so I'm going to stick with that. Anyway, compared to modern fractions, these fractions would all have a numerator equal to 1. So numbers like 1/2, 1/3, 1/4, etc. That's interesting. But what about fractions like 2/3 or 3/4? It seems pretty limiting if you can only have 1 as your numerator. Like, how would the ancient Egyptians measure out their pretcho cheese? Yeah, okay, that's a good question. And it does seem pretty limiting, but the ancient Egyptians were very clever mathematicians. And instead of writing 3/4 as 3/4, they'd split it up as 1/2 plus 1/4, and then use that for their calculations. Oh, I see. So 2/3 would be, well, wait, couldn't they just write it as 1/3 plus 1/3? Well, they could have written it that way, but that's not how they did it. Each of the fractions was required to be different, so none of the denominators could be repeated. Okay, well, let me see if I can figure out how they would write 2/3 then. So 2/3 is bigger than 1/2, so they would call it 1/2 plus something. To figure out what that something is, I could subtract 1/2 from 2/3 and see how much is left. The common denominator is 6, so that would be 4/6 minus 3/6, which is 1/6. Would they have said 2/3 by using 1/2 plus 1/6? That's right. Now you've got it as a sum of 2 different unit fractions. And that's the name of the game here. Fractional quantities were expressed as sums of distinct unit fractions, usually ordered from largest to smallest. So, for example, the fraction 4/5 would have been expressed as the sum of 3 unit fractions, 1/2 plus 1/4 plus 1/20. I think that's the first time I've heard you say unit fractions. So just so we're all on the same page, can you tell us what that means? Oh, sure. A unit fraction is a fraction whose numerator is 1 and whose denominator is a positive whole number greater than or equal to 2. Oh, so the fractions you mentioned before, 1/2, 1/3, 1/4, etc. Okay, well, now I have a question. Can every rational number be written as a sum of unit fractions? They can. And in fact, you've already given us a hint at how to do it. I have? I mean, that's right, I have, haven't I? Okay, so should I remind you of your brilliant insight? Oh, yeah, by all means, please do. If I do it, it'll just seem like gloating. Okay, right. So, well, when you showed us that 2/3 is equal to 1/2 plus 1/6, the first thing you did was notice that 2/3 is greater than 1/2. In other words, you found the largest unit fraction that could fit inside 2/3. And then you subtracted it from 2/3 to get a remainder of 1/6. And since 1/6 is itself a unit fraction, you were done. Wow, Pete. Sounds like I did more than just give us a hint. I mean, that's the whole kit and caboodle right there, isn't it? Okay, but hang on a second, genius.
Genius! That's what it is. Sheer genius!
Let's use your little kit and caboodle on 3/7 and see what we get. So the biggest unit fraction, less than 3/7, is 1/3. And if we subtract 1/3 from 3/7, we get 2/21, which means that 3/7 is equal to 1/3 plus 2/21. We don't end up with a sum of two unit fractions. Okay, but I don't think that's a problem. We can just split up 2/21 as a sum of unit fractions and then substitute that answer back into our expression for 3/7, right? So let me just do that real quick. The biggest unit fraction we can use is 1/11. And if we subtract that from 2/21, we get 1/231. Okay, I got it. 2/21 equals 1/11 plus 1/231. That means that 3/7 equals 1/3 plus 1/11 plus 1/231. You're right. That does give a unit fraction expression for 3/7. But I hate to tell you, I have it on good authority that 2/21 would not have been written as 1/11 plus 1/231. It wouldn't? Nope. And you're probably not going to believe this, but an ancient Egyptian told me that 2/21 is actually 1/14 plus 1/42. An ancient Egyptian told you? Sounds like the old Nigerian prince email scam, Pete. Don't send them any money. Okay, I promise, no money, but it's true. So have you ever heard of the Rhind mathematical papyrus? It's a very old papyrus scroll full of Egyptian mathematics, and it just so happens to contain a table of expansions for 50 different fractions of the form 2/n. The table starts at 2/3 and goes up from there. 2/5, 2/7, 2/9, all the way up to 2/101. Whoa, really? So we actually have an ancient artifact that shows us how Egyptians were writing their fractions at that time? We do. The papyrus, which is more than 3,600 years old, contains a wealth of information about the kind of mathematics the Egyptians had developed. And check this out. In the opening section, the author, a scribe named Amos, wrote that this book presents, quote, accurate reckoning for inquiring into things and the knowledge of all things, mysteries, and secrets. Ooh, I love that. What a cool way to describe math. Yeah, I love it too. Well, a large section of the papyrus contains a table of fractions, the so-called 2/n table. And in that table, the fraction 2/21 is written as 1/14 plus 1/42. So an ancient Egyptian really did tell you how to write 2 over 21. Cool. So, okay, circling back, I guess an ancient Egyptian would say 3/7 equals 1/3 plus 1/14 plus 1/42 then. Exactly right. But now I have another question, Pete. If the ancient Egyptians didn't use fractions with numerators and denominators, then how did they even use the table to look up the unit fraction sum for these 2 over n fractions? Like, if you don't have numerators, how can you even express the idea of 2/3 or 2/5 in the table? Okay, well, the table has 2 columns. The first column lists the unit fractions 1/3, 1/5, 1/7, and so on, up to 1 over 101. Notice that they all have odd denominators. And right next to each one of those fractions, in the second column, is the unit fraction sum that represents the double of the fraction listed in the first column. Oh, I see. So the second row of the table has the symbol for 1/5 in the first column, and the second column tells you what you get if you add 1/5 to itself. That's right. And in this case, the second column shows 1/3 plus 1/15, which is in fact equal to 2/5. That's pretty clever. It didn't matter that they didn't have symbols for fractions like 2/3 or 2/5. They could create whatever they needed by adding unit fractions together. Yeah. Now, I do want to mention one last thing about the table. There's something interesting in the first row. In that row, the first column contains the symbol for 1/3, as we'd expect. But instead of a sum in the second column, there's a new symbol, and it's really quite clever. It uses the same mouth symbol used for unit fractions, but it looks like it has 2 legs beneath it, one of which is about half as long as the other.
What? It's true. My right leg is 2 inches shorter.
Come on, you're just tilting.
It's like the symbol is saying 1 over 1.5, or in other words, 1 over 3/2, which happens to be 2/3. Okay, so 2/3 had its own symbol, which means you shouldn't have given away our 2/3 cup measuring cup. I guess it was a bit rash of me. And I think they might have had a symbol for 3/4 too. Dude, that's it. You're banned from the kitchen till we get our cups back. Okay, but in my defense, once you get to denominators bigger than 4, all other non-unit fractions were expressed as the sum of unit fractions. And by the way, the Rhind Mathematical Papyrus is currently in the British Museum, so listeners can go see it for themselves in real life. In fact, there are lots of images online, so anyone who's curious can easily take a peek. We'll put a link to it in our show notes so you can check it out straight from there. That's a great idea. So if 2 over 21 can be written as 1 over 11 plus 1 over 231, or as 1 over 14 plus 1 over 42, I guess that means rational numbers don't have unique expressions as sums of unit fractions. That's right. There are lots of ways to express a given fraction. In fact, infinitely many ways. Somehow I knew you were going to say that. If there's one thing I've learned from talking with you about math, it's that if something can be done in more than one way, it usually means it can be done in infinitely many ways. Yeah, okay, guilty as charged. That's true. But hey, let me tie up a loose end here before we move on. Let's go back to the algorithm we've been talking about for splitting a fraction into a sum of unit fractions. Something interesting happened with the number 3/7. After the first step, we were able to rewrite it as 1/3 plus 2 over 21, which is a unit fraction plus a remainder fraction. Now, here's the key observation. The numerator of that remainder fraction is less than the numerator we started with. Okay, I see what you mean. We started with 3/7, which has a numerator of 3, and the remainder fraction is 2 over 21, which has a numerator of 2. Yeah, 2 is less than 3. The numerator got smaller. But why is that important? Well, for 2 reasons. First, for fractions that are less than 1, like our 3/7 here, the numerator will always decrease. It may not always decrease by 1 like it did here, but it will always get smaller. And second, if a sequence of positive integers decreases with every step, it must eventually decrease down to 1. Okay, so let me see if I understand what you're getting at. If we start with a fraction that's less than 1, even if it's really crazy, like 408 over 577, we can use my brilliant algorithm to write it as a unit fraction plus a remainder fraction. And then by repeating that algorithm on the remainder fraction, we can keep going until all we have are unit fractions, and those unit fractions will add up to our starting fraction, right? Yes, that's right. Man, I really am a genius. All right, Chucklehead, but you're not the only genius around here. This algorithm was discovered by Fibonacci, who published a version of it in the year 1202 in his book, Liberace. Oh, Liberace. My grandparents used to love to watch him play piano in his sequin jackets on TV back in the 70s, but I did not know he had anything to do with math. Dude, I think that's Liberace. Oh man, I'm getting so confused with all the Achis around here. Fibonacci, Liberace, Joni Loves Chachi. There's too many to keep track of. All right, I'm going to rein in all these Achis and bring us back to Fibonacci. I want to talk a little more about his algorithm, which, by the way, is an example of a greedy algorithm, because at each step, we look for the largest unit fraction that can be used. I've never heard of a greedy algorithm before. Are there other examples we can wrap our heads around? Sure. Here's a super familiar example. So suppose you're at the store to restock your pretzel ingredients. You pick up a couple of bags of pretzels and some shredded cheddar jack cheese, and the total cost is $9.63. So you give the cashier $10, which means you'll get 37 cents back in change. Now, the cashier could give you 37 pennies, right? But what they'll probably give you is a quarter, a dime, and 2 pennies. So this is another example of a greedy algorithm. You make change by choosing the largest denominations you can at each moment. Oh, I see what you're saying. So at each step of the way, you would give as many of the largest denomination of coin that you can. So the largest denomination of coin is a quarter. So how many quarters can I give you if I'm trying to give you 37 cents in change? I can only give you 1 quarter because 2 quarters would be too much. So I put down 1 quarter, that's 25 cents. Then I move to dimes. I can only give 1 dime. That gets from 25 cents up to 35 cents. I can't do another dime. Then I go down to nickels. I can't even give you 1 nickel because that would go over the 37 cents I'm trying to hit. So then I move to pennies. I give you a couple of pennies and I've made 37 cents. And every step of the way, I've used the largest coin that I can use. Is that more or less what a greedy algorithm is saying? Yeah, exactly. And listeners might enjoy thinking about the ways this example with coins is both similar to and dissimilar from Fibonacci's greedy algorithm for Egyptian fractions. After all, a quarter is 1/4 of a dollar, and a dime is 1/10 of a dollar. But the point is, in both cases, the algorithm is very greedy. And I got to tell you, Pete, when it comes to my pretzels, I can be pretty greedy too. Oh, really? I totally hadn't noticed. So we've been talking about what these fractions are and how to manipulate them. But what I really want to know now is, how did the ancient Egyptians actually use them? Well, I don't think anyone is entirely sure, but I think the short answer is this. Just like us, they used them to carry out the work of their day-to-day lives. We know the ancient Egyptians farmed, they built amazing structures, they engaged in various forms of business, and they absolutely must have used them when they built the map room at Tanis, right? I mean, when Indy stuck the staff of Ra into that hole and then that beam of sunlight shot right through it to show where the Ark of the Covenant was hidden, that was super precise. There's no way they calculated that entire thing using only whole numbers. Well, dude, as long as you know that the ancient Egyptians didn't just spend their time hiding arcs, then I think we're all good. Yeah, we're good. And this all makes a lot of sense. I use fractions all the time too, and without really noticing that I'm doing it. Like when I'm cooking dinner for my family, I sometimes have to scale a recipe up or down, for example. Or when I'm planning out my day, I sometimes have to add fractional parts of hours together to make a schedule that works. Or when I'm looking at how much gas is left in my car, I have to use fractions to mentally calculate how far I can go before I need to refill the tank. But you're right, I don't consciously think, I'm using fractions now. I just do it. Yeah, and I think the same is probably true for the ancient Egyptians. Now, let's do another example that I bet would give a reasonable illustration of some unit fractions in action. Yeah, give us some fraction action, Jackson. Okay, so suppose you have to split 3 loaves of bread between 4 people. Now, we could cut each loaf into 4 pieces and give each person 3 of the slices. And we could do that with a total of 9 cuts, 3 cuts per loaf, right? But since 3/4 is equal to 1/2 plus 1/4, we could achieve the same split by giving each person half a loaf and then 1/4 of the remaining loaf. And this would only take 5 cuts in total. And to be honest, it would probably be a more convenient way to distribute the pieces as well. Oh, yeah, I see. That's actually pretty clever. Cool. So let's do one more example. Now, we talked about pizza in a recent episode. So let's try this. Suppose you need to split 7 pizzas among 12 people. How can we do it using unit fractions? Well, I can see right away that 7/12 is bigger than a half. So the ancient Egyptian equivalent would be 1/2 plus something. And that something is going to be 7/12 minus a half. And that would be 7/12 minus 6/12 is 1/12. So 7/12 equals 1/2 plus 1/12, meaning everybody gets half a pizza plus a 12th more, which means we can cut 6 of the pizzas in half and the last one into 12 slices. You know what? That's a pretty cool way to do it. Right. Now, that answer also gives us some insight into the amounts that we're talking about. 1/2 plus 1/12 means 1/2 and a little bit more. It provides a quick way to estimate the value of a fractional quantity. So let's make a comparison to our own fractions. If I mention the decimal, and remember, a decimal is just a kind of fraction. So if I mention the decimal 0.758139996, you're probably going to think, okay, that's pretty close to 0.75. And you'd be right, it is. Unless you need the additional accuracy, you might be happy to work with 0.75 instead. This is making me think about an earlier example. We said before that 3/7 equals 1/3 plus 1/11 plus 1/231. Unless it really matters to me, I can think 3/7 is pretty close to 1/3 plus 1/11. I don't think I really need to worry that much about that 1/231. Yeah, exactly. You got it. And you can imagine that the ancient Egyptians would use shortcuts. They would memorize various facts for quick recall and would make various approximations in real time, on their feet, so to speak. Yeah, just like we do. For example, if I drive by the gas station and see that gas costs $4.49 a gallon, I'm going to think it's $4.50. And if it costs $4.89, I might even think, geez, $5 for a gallon of gas? Yeah, that's the kind of thing I have in mind. And although I don't know exactly how the ancient Egyptians used their fractions, I'm really confident that they would have integrated them into their daily lives much the same way that we integrate our modern fractions into ours. Well, this conversation about Egyptian fractions was super interesting, Pete. And it makes me wonder if there's a related puzzle that we might be able to challenge our listeners with. Ooh, I do know of a cool puzzle. So let's imagine for a moment that we're passing through ancient Egypt on a camel. On a camel? The two of us? On the same camel? Yeah, it's like an ancient Egyptian version of sharing an Uber. Okay, but I get to sit between the humps. Fine, you can be between the humps, okay? So we're riding along and we come across three brothers with a herd of camels. A herd? I believe you mean a Dodge Caravan of camels, but maybe without the Dodge. And we can see that the brothers are arguing about something. They're all riled up. All right, should we stop to see what all the fuss is about? We should. And it turns out that their father recently passed away and left his herd to the three of them, according to these directions. Divide my camels among yourselves in the proportion of 1/2 of the herd to the eldest son, 1/3 to the middle son, and 1/9 to the youngest son. Sounds pretty straightforward. What's the argument about? Well, the number of camels in the herd isn't divisible by 2, or by 3, or by 9. Ugh. Sounds like they're going to have to start chopping up some camels. Well, they could do it that way, but now that we're here and we have a camel of our own, we can actually help them out. How can we? Oh, I see. If the herd isn't divisible by 2, then it's an odd number of camels. So if we add our camel to their herd, now they'll have an even number that can be divided by 2. Exactly. So let's do just that. We sell them our camel for 10 pieces of silver. And as it turns out, when they add our camel to their herd, the new total is divisible not only by 2, but also by 3 and by 9. Nice. Even in ancient times, the math club guys were there to make math easier for everyone. Now the brothers are able to divide up the herd, giving 1/2 to the oldest brother, 1/3 to the middle brother, and 1/9 to the youngest brother. But guess what? What? After dividing them up, there are still 2 camels left over. And the brothers are so happy with us for helping them solve their dilemma, they give us back our original camel and the other extra one. So now we each have our own camel? Yep. And 10 pieces of silver to boot. Interesting. So here's the question, Math Club. How many camels were in the original herd that the father left to his sons? Oh, I like this one. Think you have a solution, Math Club? The first listener to reach out with the correct answer will get a shout out on our next episode. Can you tell everyone how to reach us if they'd like to share their answer, or if they have questions or suggestions for future episodes? Sure. You can reach us in a few different ways. Our email address is mathclubpodcast@gmail.com. Our Twitter handle is @mathclubpodcast. And you can now send us a voice message on our SpeakPipe page, speakpipe.com/mathclubpodcast. And that reminds me, we're still collecting your favorite math jokes for our upcoming jokes episode. You can send those to us on any of those channels, but if you'd like to actually hear yourself telling your joke on the show, use our SpeakPipe page and make sure to tell us that we have permission to use your voice on the air. Hey, Noah, I'm getting kind of hungry. Do you think you'd mind sharing some prechos with me after all? I guess so. I think I could part with 1/3 plus 1/8 plus 1/15 of them. Ooh, let's see how much that is. 1/3 plus 1/8 plus 1/15. And then I carry the 2. All right, we'll see you next time, Math Club. Bye, everyone. Catch you later.